just a bit just long title, but I will just try to to cover everything what is actually in the title during my talk. Does everybody hear me? Right? Everything is okay. You see the slides?
Yes, absolutely
okay.
fine.
Well, I will just move on. What actually is meant with everything with remote control delivery systems. And I'm actually a physicist from my background education, and actually look on many things from actually a physical point of view and what actually physics could offer us to control various micro and nanostructures remotely. Ideally, we actually should have like actually this guy who actually could manipulate with different delivery systems with actually small device. And what actually physics offers is for distant signaling is just light in visible light, but also infrared, near infrared, because it actually could penetrate deeper. It's of course actually ultrasound. It's magnetic, and in more broadly terms, actually it's radio waves in wide range of spectrum. So that actually means there are components of microstructures or nanostructures. They have to be susceptible to one or more of these physical stimuli. So and now the question is how actually could assemble those things, and then the question is, okay, what chemistry could offer us to make these delivery systems? And I have to say, I'm saying it also in chemical audience, I mean, without hesitation, that the less chemistry you do, then better. It has to, or in other words, it has to be done very wisely. So minimum chemistry modifications, because later on, whatever you do with the chemistry, you have to prove before actually you come to any clinical applications and so on. So no new molecules, or just make it very wise. They still have to keep responsiveness that actually usually chemists could offer us a lot of polymers, for instance, that actually could be responsive to various factors, self-assembly, and we do actually quite a lot with layer by layer. Actually, I mean, I actually was doing it for almost, 2 decades, and now actually we know the limits of this technology. But what actually I want just to say that it's a good thing in layer by layer, right? I guess you're polymer people, I mean, you all heard about it, but it's combined with other encapsulation technology. If you actually consider layer by layer per se, it's tedious, it's actually time consuming, it's not much actually scalable, but it can be combined if you want actually to impregnate your function to other capsules. You could use electrospray, various emulsions, whether actually oil and water, solid and oil and water, microgel or micro beads, right? And then actually you could put actually a couple of more layers, right? That actually could bring your functions on there. And if you talk with people who actually do drug delivery systems, I think the 95% of them would say we have like a molecules that actually could bring our entire vesicles to some particular sites, but this does not work, right? And now there are more reviews that simple ligand on the surface might not actually work. We actually more focus on physics, right? To make something that actually makes your responsiveness from remote physical signaling, like a magnetic particles or metal particles could actually absorb the light. And of course, as a layer constituents, you could explore many things in such structures within the multi-layer buildup. But as I said, few layers could be quite enough. Well, you probably actually saw that magnetic materials actually, well, they actually move to the magnet. It's sort of just sort of the obvious things. I mean, you have the capsules, right? They actually move to the magnet, and the capsules are actually made of the polymers that are actually degradable, but they have sandwich magnetic nanoparticles, and actually they could nicely actually move to the magnet. And if actually they get together, they actually form like a bigger magnets, right? The capsules together, so they actually respond more quickly to the magnet. If you have incorporated, this is actually a bit old video, but I like to show it because actually it's quite, people like actually to see it. If you have your capsules with something that actually responsive to the light, for instance, like silver nanoparticles, you actually focus to single individual capsules, and actually you could see that where actually you focus your light is actually open, while others remain actually intact. If you ultrasound, while composite materials, if you have composite materials, they respond to mechanical stress, which is actually ultrasound. Actually, it's a bit challenging engineering task is to combine ultrasound and optical microscope, but probably you could still notice that some of the capsules, they actually came to the area of observations being intact, and upon the actual ultrasound, they actually got broken. So that what actually they have those capsules, they have polymer and inorganic component in there that make actually non-homogeneous density. That's why actually they respond better to ultrasound. Well, now just about probably most actually recent thing what we have done actually before actually I move on. I could just refer on our early work where we actually make the carbonized capsules. So actually what we do, we have the capsules and we also have the source of sugar. It's actually polysaccharide, it actually sort of entangled within the polymers in there. If you heat it up to 180 degrees, there is a carbon nanoparticles formed, right? What actually happens? The capsules make shrunk a little bit thicker in the shell, and what they have less permeability because actually they're shrunk, but they're also fluorescent. They actually could encapsulate, for instance, a dye like a rhodamine, but their fluorescence come from the carbon nanoparticles, right? So actually you have two peaks, carbon nanoparticles peak and rhodamine. And I have to say that if you look on those capsules, right, they look dark because you have your carbon obviously synthesized there, right? So then actually you could actually expect if you expose the light on such in the capsules, they actually should absorb the light, heat it, it probably release the carbon. But as quite often happen in science, I mean, you actually plan other things. You tell your students, okay, do this, and you actually should get this, but they got something different. And we actually have such in a capsules with rhodamine with carbon nanoparticles in the wall. We expose the light on 3 of those, but instead of just opening the capsules, we see they just change the color. We actually look deeper on this, and we actually find out we have a photochemistry. We have a photochemistry that in the presence of the carbon nanoparticles, I mean, rhodamine actually undergoes their cleavage of the bonds and change we have another dye actually. Instead of rhodamine B, we have rhodamine 101. So it has a different spectrum. So actually we actually could switch those capsules from one color to another. Well, you probably might say, okay, there are many photo switchable things. Okay, but the good thing in these capsules, they actually can be easily internalized by the various cell types. In our group, but also in some other groups, I mean, across the world, who actually do this layer by layer capsules because they actually solved. They could easily get internalized inside the cells. So you have those capsules internalized, and capsules could reside inside the cells, I mean, for weeks, actually, as long as you could maintain your cell culture, your capsules will still there. But they internalize the capsules, and then actually you could switch it, right? And actually the cell will leave with another colored capsules. And of course, actually you could play with this, right? You could see the time and lapse video. So the red is our capsules. Cell eventually might take 2, might take 5, might take 10 of those capsules, and then actually with the light, you actually could switch certain number of those capsules, right? And they still reside inside the cell. So you have multiple combinatorially, you have a multiple coding of it's like in a barcode. I mean, you actually could label your cells and actually see how the cells could track. In this particular case, we actually take the myocytes, C2, C12 cells, and actually we label many of them. Well, we could label many of them, but actually we were interesting just to probably to monitor maybe actually 5 of them. So actually you could see, well, you actually could focus on, you could see how actually the cell moves, being having the internalized capsules. And well, actually we monitored up to 9 hours, I mean, all this. And actually later on we came and analyzed how far actually our cells moved. So of course we always have this imaging analysis, right? We actually could see that here on this slide what distance the cell moves. It's just a little bit better view. And actually you might notice, I mean, in the cell population, right? If you look on the cell type, on the cell population, some of the cells, they just stay, right? They do not move. They do just stay for various reasons we don't know. But some of the cells, they actually eventually, I mean, travel quite a lot of the distance, right? Over those hours. And well, I'm not a cell biologist. I mean, actually, we speak with the people, we actually get, talking to that. And there is certain reports now, the cells, they live the social life, right? Like people do. So there's always cells who actually respond first. It's just like a leader. I'm not talking the actual political leader, but they're a leader. It's about a few percent of them. They actually respond fast to whatever stimuli you have. And then actually there is other like cell followers that actually could make another 10% of them. They just follow them. And actually majority of the cells, about 70% of them populations, people just call it the cell citizens, right? They just follow, right? Okay, so but this is the case. You actually with this technique actually you could probably change and see track cells. I mean, and then actually later on you actually could separate and see how they progresses. So far, people label the cells just between two colors, right? Now you could and you need genetic modification of cells. Here you don't need it. Okay. Well, another way of remote responsive capsules. Well, simple things is a magnetic field, right? I mean, you could have fluorescent capsules and also with a magnetic field. You actually mix it with the blood. You pull it from the bloodstream. You apply the magnet to near the capillary. No surprise, cells. The capsules just attached to the magnet. It's no surprise. You remove the magnet, and they actually will be washed with the blood flow, right? Okay. Nothing surprise with a magnet attached, no magnet washed away, nothing keeps them on the wall. The situation becomes a bit different than you do it in vivo. So if you actually take the rat, so this is mesentery of the rat, so rat is just that big, right? And so you need to take the vessel of the living rat going outside the body, because you have to put the optical microscope on them and the magnet at the same time just to monitor it. You have such sort of desk where actually a rat is actually placed. A rat actually could live for some more hours after that. Well, it's a bit painful, but okay, that's what actually you could have. And I hope the video could work. Let's see. Yes. Well, this is a vessel. You see the flow of erythrocytes, right, in the transmission light. So the flow, you put the magnet, okay, something in the shadow, and then make sure we switch it to the fluorescent light. First moment you see nothing, and then make sure through the catheter we have actually injection of their fluorescent capsules. And now you see they actually moving. This just injection in the blood flow. You see how they are moving, and with the time we have some of the accumulation of the cells of the capsules, especially near the sites where we have bifurcations of the vessels. So actually you could actually track and retain some of the magnetic capsules near the magnet, right? Where actually you place your magnet with a certain probability. And we also found that they do not stop the flow of erythrocytes. Now it will be switched back to the transmission view, and it happens because actually the capsules get actually embedded in the cell. So inject the cell, put the magnet on one, you inject it in one leg, you put it on the magnet somewhere, and actually you could monitor how the capsules actually get distributed over the body. So we do know with the time, initially we have quite a big of them in the lung, in the liver, actually no surprise, but actually what we do know, in 1 week, we almost have all the capsules actually gone, right? So they actually get degraded because the polymers, the capsules made of are degradable. The magnetic component is iron oxide, it also get degradable. In 1 month, there is actually no traces whatsoever. In case of the magnetic field, if we put the magnet on near one leg, inject to another leg, we actually could see some of the accumulations in the opposite leg. You can't do much about this central part because it's actually liver, and liver takes the most. Whatever you do, whatever you make any surface modifications, liver will take the most of them. But at least a certain percentage you actually could get where actually put your magnet. At least it's actually better than many other techniques with chemical modifications of the capsules. Okay, so mice is still alive after all of this. I also have to say that if you have a cell, and actually cell internalize the magnetic capsules, so cell is about 20 microns, right? Capsules could be actually 4 microns, and actually if it just sort of internalize their the capsule cell becomes magnetic. So you actually could apply the magnet and actually you drag the cells, the entire cells, right? Because they actually anchored with the magnetic materials which is actually inside them. We have done with various cell types, as I said, also including the stem cells. So stem cells, they actually could have quite substantial number of the capsules internalized. There is very minor effect of their viability. You need just very few capsules per cell to make the entire cell magnetic, right? And then, well, you have the labeled cells. The gray is just labeled as just capsules. Gray is actually cells. Actually, with the magnetic sorter, you could separate the capsules, cells with the capsules and without. And the thing with the stem cells is that you could manipulate these stem cells with the magnet, but they have no effect whatsoever on their further ability to just proliferate, differentiate to the different cell types. So there is no effect on that. We also studied some other things. So actually cells could feel once actually internalize the capsules. They actually move a little bit slowly, right? It looks like they got a magnetic backpack, something heavy stuff, so they do not move faster, but they still could differentiate, they still could proliferate and get actually divided on daughter cells with eventual distributions of the capsules between them. So, and then actually conceptually, you could actually have their macrophages, own macrophages, I mean, taking from their own body, impregnate these macrophages with the capsules and re-inject them back, right? And re-inject them back, no immune response whatsoever because it's actually its own cells, and actually the cells could actually get recruited, right? And this is actually first experience that we have done so far with the manuscript just accepted. We actually saw that these macrophages, at no surprise, they actually get to the liver, but actually we could find them. We could actually see there how actually we could track our macrophages inside the body, right? Using the in vivo imaging and ex vivo analysis as well. So, but I have to say, capsules actually is nice things, but it's still quite far from clinical applications. And talking to the doctors, I mean, just they want simple things. They want simple things, right? Simple, robust, and reliable things. And actually, we move from the capsule to something easier, something like you do instead of the capsules, you make the film. We call it like a microchamber. It's simple like a lithography approach. You could make imprinted structure, you could coat it with a film, and you could actually make such sort of, structures, right? Chamber, right? In those chambers, you don't need a multi-layers for this. Actually, it's 2 layers is enough. Something can be sandwiched between them, right? But advanced is you could easily encapsulate many things, right? You have imprinted structure. You put actually 1 layer of the polymer. You put the drug or put the powder. It gets within the wells. You seal it with another layer. You actually peel off your film, and you have your stuff encapsulated. And the thing is, if you have, for instance, hydrophobic polymers like polylactic acid or derivatives of polylactic acid, you have inside them, you have precipitates of your drug, but you also have air bubble, right? You put it in the water, you still have it air bubble. What is good in air bubble? It's extremely responsive to ultrasound. You apply the air bubble, ultrasound, and all these microchambers get actually ruptured. Whatever you encapsulate inside actually get released. So this is actually 2 videos. We have the film with the chambers with actually drug dye loaded them. You put it in an ultrasound buff, and immediately your dye is just releasing, right? As soon as actually switch on your ultrasound buff. So very robust technology, right? Well, we actually encapsulate epinephrine, which is actually adrenaline, in those chambers, right? This film is actually precipitated, so that's how actually the film looked like. We actually incorporated into the mice. So we took like a thin things, 5 by 5 millimeter, implanted into the mice. Mice actually lives them for 3 days, doesn't know anything, no feeling of adrenaline whatsoever. In 3 days, you actually apply the ultrasound to the mice, which actually always could be done remotely, and you have a change in the blood flow, sudden change. So then actually could incorporate something and then actually introduce this into make a chemical injections from the distance, right? So that's various type of what actually chambers that actually we could have. It's all, well, people who actually do the lithography, whether the semiconductor lithography or actually laser ablations, there is actually no limit what shapes of those structures you could do. And initially we actually moved, okay, we actually could coat the coronary stents. And but we actually dropped this idea, right? We actually published a paper, then dropped this idea, because talking to the doctors, the problem is if it degrades, you always have the coronary stents degrades, you have a debris, and actually it's quite dangerous, right? Okay, we actually may move to other things. We actually coated, we got actually clinical approval for medical devices actually implanted anyway in the operation, because we use the polymers that actually proved. We use the drug, which is already doctors actually use. It was actually relatively easy, not easy, but still possible. And we have done so. Go for a local ethical committee. And we have actually done it for urethral catheter. So it's just like this. It goes into patients, get blown. And then actually the doctor actually sees with ultrasound imaging various catheteries. They actually increase the intensity of ultrasound, chambers actually open, and anti-inflammatory drug actually get released into the tissues, right? All manipulations 10-15 minutes, right? So it's just about 10 patients who actually so far passed for this procedure. Another one is just also in Moscow City Clinical. It's for biliary stents, and biliary stents, you don't need trigger for this. It stays in the patient for 4-6 months. Film actually degrades, and whatever you encapsulate drug is actually released. Well, and just in the end, because actually I always do the particles, right? And actually, instead of just making the chambers, right? We actually made the chambers, but then we actually separated each chambers out of them, right? So chambers are easy to load because you have the open wells, but at the same time, you could actually separate it later to individual capsule. And I have to say, it's, well, people who actually could know what is actually dumplings, the China, ravioli in Italy. There's also Russian name pelmeni of that, which actually came from Kazakhstan, but doesn't matter. So really simple protocol how it's done. And the cooking, you actually could do it in a micro scale, right? And get the structures, right? So you actually sandwich meat, right, proteins, right, between two polymer layers. So it's actually your pasta. Well, it just, whatever actually lithography you have, right? Then actually the size of your printed capsules you have actually on the same size, and shape is control, size is control, everything is control. So it's just another encapsulation approach what actually we have developed. Well, and then yeah, that's just another you know, that's truncated pyramid, you know, what actually we have done using this templating. And so in the end, I just would like to thank, I mean, people actually with whom actually I'm collaborating. Also, it's just some outing of our group. And thank you for listening to me.
Okay, thank you so much for